Welcome everyone, and thank you for joining us on today's webinar. My name is Laura Roberts, and I'm the Ava Marketing Manager at PDS Group. For those of you who may not be familiar with PDS Ava, we build cloud-hosted software which addresses key limitations in existing reservoir modeling workflows. Before we get started, I'd like to introduce our speaker today, Dan Hemingway, who is a senior geologist in PDS's Ava team and currently supporting the development of Ava Clastics and Ava Structure. Dan joined PDS earlier this year and currently works as a senior geologist across our Ava product range. Dan spent several years as a senior consulting geologist for RPS in London on a range of projects focusing on the generation and audit of static and dynamic reservoir models. Before that, Dan worked for RDR, now part of Schlumberger, as a structural geologist involved with the development and commercialization of the structural and fault analysis module in Petrel. Dan holds a BSc in geology and an MSc in structural geology with geophysics from the University of Leeds. Today's webinar will focus on understanding how the quality of our structural interpretations impacts our understanding of reservoir compartmentalisation and the resulting reservoir models. This is an important topic because reservoir compartmentalisation is a major uncertainty in the appraisal of petroleum reservoirs. Poorly understood reservoir compartments and the connections between them affect the volume of movable oil and gas in a given field and can have serious impacts on field viability and profitability. In this session, Dan will show us how that uncertainty and impact can be directly derived from our interpretations, how we can generate alternative plausible fault networks, and how to use those to quickly generate correspondingly fault reservoir models. Before we jump into Dan's presentation, please note that we've allocated time at the end of the webinar for questions and discussions. If you wish to ask a question, please type it in the question box in your GoToWebinar control panel. You can type the question in at any time throughout the webinar, but we'll only answer questions at the end of the session during the Q&A. Also, a reminder that this webinar is recorded and will be made available to attendees 24 hours after this webinar finishes. And now, without any further ado, I'll turn the time over to Dan.
Thank you, Laura, and thank you all for joining us this afternoon. Welcome to the webinar. As Laura mentioned, we'll be looking at structural uncertainty in reservoir models, which I appreciate is a very broad title. So I'll just introduce kind of where we're going to go with the webinar with a bit of housekeeping. So to start with, we'll be just looking at the introduction to uncertainty within the subsurface. So what do we class as uncertainty? How do we address it currently, and what are the ways in which we can improve it, specifically relating to structural uncertainty and compartmentalisation? The second half of the webinar will be live demonstration within Petrel using one of our products, Ava Structure, to essentially address that uncertainty within our reservoir modelling workflow. And then we'll have some time at the end for some questions. Okay, so just to sort of take a general holistic view of how we approach subsurface uncertainties when we're building our reservoir models, we tend to identify the key uncertainties that we know affect our reservoir. And then from these, we tend to build up multiple scenarios that honor the known data in order to test the impact that these key uncertainties have within our models. And typically, these uncertainty workflows tend to be based on single structural models, so just an isolated structural model, whereby internal reservoir parameters can be tweaked and modified with what we call relative ease. And obviously, the reason for that then is that the generation of multiple structural models, or even just a single model, is an onerous process. It involves reinterpretation in a seismic domain, which can be exhaustive, and the repetition of what we know to be laborious structural modeling workflows such as pillar gridding. And I'll just draw your attention here to one of the ways that we'll be addressing this uncertainty is using Petrel 2018. And the reason that we do that is the introduction of depot gridding into their workflows. So that's a new structural modeling workflow whereby you create a structural model in depositional space rather than geospace, or the space in which we see it at present. And by doing that, it allows us to capture more complex structural configurations, and more importantly, it allows us to do this in a more automated way. So we can integrate these more complex geomodels into the reservoir modeling workflows in a more automated fashion. So we'll demonstrate using Ava Structure how we can take a single interpretation base case and then build up multiple plausible structural models to automatically integrate them into those workflows. And this obviously then allows us to incorporate that structural uncertainty to be routinely incorporated into those workflows. Okay, so just sort of taking a step back and just addressing what we know to be the uncertainties within the subsurface. We tend to group these into two main themes, the first of which being the in-place volume. And then we can essentially break that down even further into things like the gross rock volume, what's the tank volume, and also what's the hydrocarbon, the fluid volume within that tank. Looking specifically at gross rock volume or GRV, we're looking at the input parameters that affect that tank or the total volume that we can contain hydrocarbon within. Things like the horizon positions, both the top and base, the fault position, and also things like the depth conversion uncertainty associated with that. And then finally, the fluid contact. So these can all be integrated and built into GRV workflows to essentially give us some uncertainty on our tank volume. We then tend to move forward to the hydrocarbon volume, look at things like facies distribution, petrophysical population, and saturation height function, again linked into a uncertainty workflow. In an ideal world, we would link these all together and have an integrated workflow that addresses all of these key uncertainties independently, but at the same time within a stochastic workflow. But what we often see is, due to that time constraint and the laborious effort that's involved in generating our structural model, is that the GRV analysis or GRV uncertainty is anchored on that single structural model. And it's this single structural model that we then link into our hydrocarbon volume uncertainty and then take that forward into things like a more dynamic analysis of uncertainty. So the second group or theme to do with uncertainty in the subsurface is that recoverable volume. So what are the things like the in-place volume that we've just looked at? Other dynamic properties like the aquifer support, relative permeabilities, aquifer pressures, etc. But more importantly, and this is what Ava structure is designed to address, is the fault connectivity and the well count. And again, looking at that structural configuration, we always tend to see that fault connectivity is an isolated case, as a single structural model. But as geoscientists, geologists and engineers, we know that structural geology is complex. We know that geology is complex, and that we typically have other variations of that single structural model that most likely exist or could exist based on our interpretation. And in reality, we should be feeding all of these models into that fault connectivity and integrating the whole workflow. So as I said, I'll demonstrate using Ava structure and the functionality within Petrel how we can remove that tie to the single model and integrate all of our different plausible models into that uncertainty workflow. Okay, so just moving on then to look at structural modeling uncertainty and what, in terms of Ava structure, what do we mean by structural uncertainty? And the problem that Ava structure is designed to address is uncertainty in reservoir compartmentalisation, due specifically to uncertainty in the fault length, fault tip estimation, and then because of that, whether or not the faults connect up. So what drives this structural uncertainty then? Obviously, we all know there's imaging or there's limitations with seismic resolution, seismic imaging, and noise associated with both the acquisition of the seismic, the velocity model generation, the processing, and the general imaging of our subsurface structures. The second of which is the geological complexity. Again, going back to what we know as geologists going into the field, we know that we have geological complexity that exists at or below the seismic imaging limitation. And through no fault of our own, we have to live with it, and we just need to incorporate this into our modeling workflows. Okay, so how does that structural uncertainty impact our models? Number one, of course, is the gross rock volume, looking at things like top structural uncertainty and flexure at and around the faults. It's simply a variation of the tank. It's not that comprehensive an analysis of the uncertainty associated with what we know to be structural uncertainty. What's more important, however, is the connected volume. So how much of that total in-place volume becomes essentially movable between the fault compartments. And we do this in two ways. Obviously, there's well-established workflows in juxtaposition of faults in analysis, where we can do things like shale gouge ratio and calibrated column height predictions. But these tend to themselves always be anchored on that single structural framework configuration. If we don't address the uncertainty associated with the structural model in the first instance, then we're not going to get the subsequent steps right. So Ava structure is in place to address this structural framework configuration uncertainty and compartmentalisation uncertainty at an early stage within the workflow. And I'm sure we're all familiar with why we're interested in understanding more about the uncertainty associated with this compartmentalisation. Again, number one being the gross rock volume, but more importantly, the connected volume. So Compartmentalisation specifically, we're looking at things like the total recoverable volume. So how much of that total in-place volume can we then extract efficiently in terms of compartmentalisation itself, but also the localization of flow around the tips of the fault. So how segmented is our reservoir and how is the flow going to behave based on the connection of our faults? And ultimately, these all influence well count and well placement and ultimately lend themselves to costs. So as much as the gross rock volume in the in-place is important, the extraction procedure and the connected volume becomes far more important when we're analysing the efficiency of our reservoirs. Okay, so just to break it down then to look at the resolution within the subsurface, I'm very quickly just introducing the concept of resolution as scale when we're building our models. So we've got a simple horizontal axis and a vertical axis that you can see are not to scale, but it's just to introduce the concept. Overlay onto that vertical seismic resolution at about 20 meters and our typical bin spacing of our seismic volume of about 12.5 meters. And you can start to see the resolution at which we're going to be missing data, missing information that isn't being integrated into our models. We tend to carry out seismic interpretation above these resolutions, so above 20 meters and above 12.5 meters. Increase that to 2D, you increase the vertical spacing, you probably also increase the vertical spacing and reduce the clarity of the interpretation. Now, when we're building our static models, we obviously have a phase of upscaling where we move to sort of out of the bin spacing increment to something more manageable in our geological models, like maybe 50 to 100 meters, but we downscale the vertical resolution. There's then obviously dealing with the dynamic elements. We then upscale both horizontally and vertically as we move through to something that can be more manageable within the simulator. So already we can see there's 3 phases of upscaling occurring from the seismic interpretation through to the static model and into the dynamic model. And then we need to ask ourselves, well, actually, what are we trying to capture? So how much of this geological complexity that we can see from things like an outcrop is honored by the dynamic model, the static model, and how much of that information and that integrity of the model, the geological integrity, is lost during these phases of upscaling. And again, looking down in this below the seismic resolution, this is a field photograph from the northeast of England, Northumberland. It's a very good exposure of shale gouge ratio. Looking at the scale, this is a person here, it's about 2 meters. So this entire section would be captured within maybe 1 seismic trace, if that. There's some subseismic scale deformation, there's some diagram folding into the fault that we're not going to be capturing. So all the questions we need to ask ourselves is, how is this complexity being translated in terms of an uncertainty parameter moving through the workflow? Okay, and just staying on the imaging topic then, we need to ask ourselves the question of what do we actually image when we're doing our interpretation? Is it the actual fault? Well, the actual answer is no. And the reason for this is because of the way that the seismic waves propagate into the subsurface. And that means that we tend to interpret faults from diagnostic indicators such as reflection terminations. So we're looking for an acoustic impedance contrast in our horizons, whereby we can pick out those key top or base reservoir horizons. We rely on these, or the termination of these reflectors, to indicate our hanging wall and footwall cutoffs. We never actually image the fault due to the high angle intersection of that fault with the propagating seismic wave. So we already know that we're not imaging that. We then have the impact of noise and Fresnel zone imaging. Again, as we intersect the fault with our propagating wave, we have Fresnel zone imaging. We lose coherence within the wave, and we attenuate a lot of the seismic energy. We lose a lot of that energy as it hits that fault, and this has the impact of obscuring the fault image even further. So therefore, those parts of the fault that exist both at or below the seismic imaging resolution are not mappable using conventional interpretation techniques. There's nothing we can currently do about this. Techniques are getting better in terms of acquisition and processing, but it's this limitation that we need to take into account when we're addressing uncertainty in our models and keep in the back of our minds that geological principle that we're trying to honor as we move through that geomodeling workflow. Okay, so just picking up 3 images then. These are actually from the same fault. Some of you may be aware of, familiar with this fault. This is the Moab fault in Utah in the USA. So this image here is from Bartlett Wash. You've got the Moab fault coming through in here. You can barely pick it out in this image, but you've got some folding or faulting in the footwall within here, and the development of quite a pronounced fault core or fault lens within here. And then on this, if I put on my seismic wavelet, this whole image approximates about 100 meters, and start asking the questions of what are we actually imaging when we're seeing this. We might pick out an acoustic impedance contrast in the hanging wall here, maybe something within there to pick out those terminations, but we're never really going to be mapping that fault core. There are advanced techniques in which we can start to refine this down, but realistically, this is going to appear as an offset horizon at best within our model. There's also some deformation in the footwall here in terms of deformation bands, but again, by no means at a scale that we'll be able to capture those in our seismic imaging. Okay, moving to the right, we have the same fault, different image, different location. This is just outside Arches National Park, and you can see that this is a relatively segmented fault with a series of splay faults coming in here, antithetic, synthetic within this main sandstone unit. And if I turn on again my seismic wave just to bring in what we're actually imaging, we're down at the 10-meter scale. And this, what we call subseismic scale faulting, you need to ask, what are we actually capturing? What would this pick out? It may pick out a simple dip in the reflector, it may be an amplitude dim, it may be a slight bend in the reflector, but realistically, this sort of deformation at this scale is not going to be captured by our seismic imaging. Again, looking at things not only in terms of juxtaposition, but also the way in these faults are configured. So looking at the deformation that's concentrated around these low throw parts of the fault, which is why I bring on ourselves to the right picture, which is a fault core. Again, the same fault, relatively low displacement. You can perhaps just pick out a pen here for scale. By no means suggesting that we'll be able to pick this out, but just for reference at the sort of meter scale to demonstrate that relative to our seismic wavelet, this is a very low throw fault, sort of subseismic scale throw, yet you can see the extensive cataclasis, the extensive precipitation within these deformation bands, and that's been generated during deformation, which essentially is going to restrict this fault to fluid flow. So again, the question is, how do we address these sort of things in our model? The output of this really, of the slide, is just to demonstrate that structural complexities cannot be captured, these sort of low throw parts of the fault, the low throw segmentation, but also the intense deformation at the fault core that exists below the seismic resolution cannot be captured using our seismic imaging. But these low throw parts of the faults are important. Even though they're not resolvable within the seismic data, you can clearly see that this is going to have an impact on our flow. And it's these areas, these low throw parts of the fault, that can restrict fluid flow. So the result of this, obviously, is that seismic interpretation, as I'm sure we'd all agree, is inherently uncertain. There are various plausible structural configurations that are possible and likely within the resolution of your base case interpretation. So take this fault, for example, you may pick one through here, but there are a bunch of different interpretations that can be made as you move from this footwall essentially down to the hanging wall in here. Okay, and then just putting that into practice then, so how do we tend to address this issue with sort of subseismic scale faulting, fault tip estimation, and fault tip propagation within our subsurface models? Again, this is the Delicate Arch in Utah. For those of you that have been here, this is just taken from the walking down the road to the car park. From the car park, sorry, you can see in here, and this is a great exposure because it shows two relay ramps. It shows two faults building a relay ramp through in here. You can actually walk directly up this relay ramp. You can see all the deformation within the ramp itself, as well as the deformation on the two fault scarps within here. But you can walk all the way up the ramp, round behind the rocks, and then you're up at Delicate Arch. So let's just plot the footwall and the hanging wall cutoffs for this fault. Both faults are dipping towards us. And again, we've got the footwall cutoff and the hanging wall cutoff of the secondary fault. And as I said, that's forming a relay ramp. In this case, it looks as though it's a soft link relay ramp, and perhaps we have some deformation in here, but it's not distinguishable from the fault flow profiles. Again, let's put on our seismic wavelet. If we're thinking about what we're imaging as we do this, we perhaps, if we had a sort of overlying softer unit in here, we would be imaging acoustic impedance contrast to pick out the hanging wall and the footwall cutoffs in here, both at this level and this level. And if we think about what happens as we get down to these lower throw parts of the fault, so as the seismic wavelet interferes with sort of the tuning thickness between the hanging wall and footwall, we know that we're not really going to be able to image anything lower than this, anything lower than about half the seismic wavelet. And that's what we define as our seismic fault tip. Yet in reality, we can see from the fields that we have what we know is an effective fault tip. Essentially, this is the minimum mapped displacement discretely on this fault. And that you can already start to see that this is some way from the seismic fault tip. The reason we call it an effective fault tip is because we have a process zone in front of our faults. And this can be defined or observed as either a discrete slip surface, it can be a series of deformation bands ahead of this, or it can be sort of micro cracking. There was a good study done here, or various studies done on the deformation bands associated with relay ramps, and then simulating the effect of this up through in here. So we take the seismic fault tip and we approximate where the fault itself is going to terminate within our geological model or our subsurface model. Is it here, or is it somewhere but in between? And the way that we can analyze this is using fault throw profiles. So just measuring the distance along the fault, and then measuring the displacement or the fault throw. In this case, we're looking at the fault throw, the vertical component of displacement. And we can plot the fault throw as it decreases down to what we know as that seismic fault tip, again corresponding to the area of tuning thickness. We then need to do some propagation, linear regression analysis, to identify perhaps where that fault tip may be. But again, this is an estimation. It could lie anywhere within this region. It could be interaction at other faults, etc. But we just don't know because, as you can see, the seismic resolution sort of finishes here. Okay, so just to put that into practice, we're going to run a quick poll for those of you still with us. And essentially, this is a top structure map from a geomodel. You can see we've got this fault in here called fault A. We've got a production well, and we've got the fault throw profile associated with this with that fault. So just distance along the fault and displacement. So the question here is based on the above map and the fault throw profile and the concept of fault tip propagation that we just introduced previously. How far would you extend this fault tip to the west? So the options are about 200 meters, 200 to 500 meters, more than 500 meters, or if you haven't got a clue what I'm talking about, select the bottom answer. Okay, so I'll pass you back over to Laura.
You should now be able to vote for the option that is that you think is correct by clicking directly on your screen. Not everyone has voted yet, so if you haven't done so, I'll give you a couple more seconds and then I'll be closing the poll and showing the result. So of those of you who voted, you believe that the throw profile will extend less than 200 meters, and that's a unanimous vote.
Okay, excellent. Thank you, everybody. That's interesting that you should choose the lowest one, so 200 meters being about here. And just before I give the results to this, I'm just going to introduce again another concept, another problem that Ava Structure is designed to combat. And just to explain what happens when we model. So again, going back to the resolution, we go from a bin spacing of 12.5 to about 50 or 100 meters grid spacing. In order to accommodate this change, this upscaling, we tend to delete horizon near the fault. So I'm sure we're familiar with step out distances. We remove 50 to 100 meters away from the fault, and then we project into the fault from the horizons to get our footwall horizon cutoffs. We also employ various periods of smoothing, and both on the fault and both on the horizon, which essentially degrades the image that we're looking at, degrades the representation of the fault horizon cutoff. Well, indeed, we want to be capturing the fault as accurately as possible based on the interpretation data. And then in terms of fault tip extension, if any, do we do it? We can do it automatically at an arbitrary uniform extension. So up in here, you can see the patrol default is about 50 meters. We can do it manually based on these single case regression cases, but crucially, these cases are done on regression cases that are already misrepresentative or inaccurate. So just looking in here, you can already see that we've removed a lot of data and the fault throw profile is closing up far too quickly. If we were to look at the interpretation data, we'd get a much better representation of what the true fault throw was there. And that defines essentially this slope that we're looking at on this smooth, misrepresentative fault throw profile. So those of you that suggested 200 meters, which comes down into here, obviously based on perhaps this slope, that seems reasonable. But in reality, taking the full fault throw profile into account and taking the raw interpretation, what we actually see is an extension of this fault throw profile up to about 1 kilometer subseismically from that linear regression analysis. If we look at the Petrel default of 50, it's tiny. It extends no further than maybe this closing contour. So again, if we look at this fault that we were extending, this fault actually closes up to this kink in the reflector. I've modified this and taken this out, but it links itself up to this west-east fault, not only in the west but also in the east. So where we had a closing contour defining our trap geometry within here, that now becomes redundant, and the actual fault itself, or the trap itself, is controlled by these two structures. You can see these fault tips overlapping. There's actually a linking relay structure within there. So the whole trap, essentially, or the whole area south of these two faults is controlled by these fault within here. Okay, so that's the kind of problem that Ava structure is designed to combat. So using specifically a model data, have those various phases of smoothing and upscaling applied to it. Essentially, that's an approximation of the fault throw. It's not a realistic, reliable image of the fault throw. We call that compromised because the data that we've spent so much time going into and interpreting, we essentially use the meaningfulness of that. So we tend to say that smooth approximated fault throws from the models are compromised and meaningless. When we're doing the fault throw analysis, they tend to be subjective and they tend to be opinionated. So it's just a sort of eyeball looking at the fault throw profile based on something that's already been smoothed. What is our fault throw profile? And that's what we typically see when we're doing this analysis. When we're looking at our fault interpretations, we always tend to see that we're underestimating the fault throw typics or the fault tip extensions. So using Ava structure, we use the raw interpretation that contains all of the important information required for what we call a meaningful analysis. So we're adding science back into the process by doing this objectively and by using these confidence intervals, by using cumulative distribution functions and probability distribution functions based on linear regression analysis of the interpretation data. So it moves away from the smoothed interpretations, the over smoothing, etc., and we can run this directly on the interpretation. Then, as I said, utilizing workflows like the depot gridding, we can then take the interpretation data and build it automatically into these 3D grid workflows. So I'm just going to jump into Petrel and just demonstrate Ava structure in action. So hopefully you can all see my screen. You can see here, just to introduce the data set, I've got a series of fault interpretations where I've just picked the main faults and a auto track 3D horizon. You can tell already that this is quite patchy. The auto tracking hasn't been well constrained within here, and we're missing quite a lot of data. So I've also got in here what I call, this is version 1. I call a version 4 of the same as top right vegan reservoir, where I've increased the efforts, I've increased the workload, etc., to build up a more concise interpretation. And I've also begun to start interpreting some of the finer scale features in here, which I call all faults. So there's two variations of this interpretation. I've got the version 1 with my main faults that I'll run through Ava structure first, and then I'll go in and run it using the more advanced interpretation. Okay, so to access Ava structure, you can either choose it from the top menu bar, the top window in here, or there's a ribbon, Ava, that contains Ava Clastic, Saturation, and Ava Structure. And if I select that, I'm just going to close the ribbon. And you'll see that Ava Structure opens as a new window in Petrel. I can use this synchronized or in tandem with my 3D grid, or I can expand it and see it in full screen view. This is the landing page that essentially gives me a quick start guide, how to use it, etc., how to get in touch, and some example cases. But it's very simple to set up. If I just select new interpretation, and the only input that we require for this is a title. So if I just call this structural interp pass 1, I can add other information like a timestamp, team, field, etc., because I'll show you where these get stored in a second. I then take my reservoir, or my horizon interpretation. I take my faults folder, and then I can press create assessment of view results. So in here, I need to define things like the depth attributes. If there's a boundary polygon I like to use, fault smoothing applied, and also uncertainty sampling. So the number of cases that I want to do in here, or the number of cases that I want to run when I'm running this linear regression analysis. Okay, and then these all get stored. If I go back in this interface here, those of you familiar with avoclastics will recognize the view that we see all of our interpretation assessments being stored in. And these give us the title, so structural interpretation pass 1, the time that it was generated, the reservoir, or the horizon, the faults, and also some qualitative indicators here like the quality and the score. But I'll come to show what they mean now. So the third domain within AvaStructure is this assess and compare, and this contains all the information that we're interested in. So the first thing that we'll see, you can see I've got structural interpretation pass 1. It tells me the horizon that I've used, the faults that I've used, and the number of cases run, etc. The first thing that I see is a quality assessment, so a score. Here we're listing the total number of faults and issues found, which are all ranked from high, medium to low, as well as some information about what that issue is. So in this case, we have increasing throw towards the fault end, so we have to assume a maximum uncertainty. The rest here being an immature interpretation are saying that we don't have enough points to create a meaningful regression analysis from our fault throw profile. Okay. You can also see that we have this dynamic map within here. So this corresponds to, again, structural interpretation pass 1. And you can see that each of these red markers identifies the issues with our interpretation. So it's just a way of flagging areas that we can go back and repeat our interpretation. Okay, but you'll see with a thumbnail in here, it's moving back onto the left, that we have a P50, a P10, and a P90. And initially, the first thumbnail that you'll see is that it tells us what's the total number of fault blocks. So in our P10 case, we're reporting 4 fault blocks. In our P50, we're reporting 11. In our P90, we're reporting 13. And you'll see the map on the right updating as I move through each of these. So staying on the P50 then, let's actually I'll start on the P10 and just go into this just to demonstrate. So this map is interactive. You can select a fault, and then you'll see for each fault we've generated a fault throw profile. I'm viewing the whole fault at present, but realistically all we're looking at is the tip or the end of the fault end, in order to do that linear regression analysis. So as I said previously, when we were eyeballing this based on our smoothed horizon, our smooth geomodel, in this case we're using the direct interpretation, the raw interpretation data, and we're applying some science to that regression analysis. So we're doing a linear regression analysis in here, just stay with the P50, but then we're also applying confidence intervals. So we've got a P90 and a P10 confidence line within here, based on that linear regression analysis. And we're also showing a probability density function that's based, it's a derivative of the cumulative density function in this green line within here. And as we saw, if you look at the fault throw, if you follow that through in this fault, I'll just zoom in. So again, these maps are interactive. As I follow this through in here, you can see that my fault throw is reducing until I get to that red dot. That's the end of the interpretation, and that corresponds to roughly our seismic imaging resolution. With my green line in my P50 case, you can see that I then reduce the fault throw. I do a linear regression analysis down, keep reducing the fault throw. The science being that I will continue to reduce my fault throw based on that linear regression until I hit the 0 meter intercept, which defines, as we saw, our effective fault throw tip. And that will happen unless I'm intercepted by another fault. So in this case, you can see that we're highlighting in red a branch line. So again, just following the base map, you can see that we're reducing until we hit that branch line. And essentially what that does in here, it separates 2 different compartments. I can toggle this active, and you'll start to see that we're now reporting things like connected areas. So just zooming in here, the fault throw reduces until it hits this fault, and at which point it tells me that I've got two distinct compartments. In my P10 case, again, looking at those confidence intervals, you can see that the regression analysis in the P10 case intercepts a 0 meter line before we hit that fault. So therefore, this fault tip should not be extended further than this in the P10 case, and it won't intercept the west to east fault to create two separate compartments. Just thinking about those patrol defaults, you remember that we had about 50 meters. Fault tip extension is the default, which is about in here. When in reality, we see that it should be extending this all the way through here in even just the P10 case. We can see that in the PDF being produced in here. So a P50 is sort of, the 50 meter extension is sort of being predicted as perhaps maybe the P1 or something in here. It's highly unlikely that it should extend only that far. Okay, so just to show that again, as we move through from the P10 to the P50, we extend and close up those faults. And as I do that, you'll obviously increase the number of fault blocks. So I'm just going to zoom out in here, and you can also see that we're reporting connected areas. So for each of these faults, we've done a linear regression analysis, and then we've extended them based on these, based on that, to create these fault block maps. So in our P10 case, we have 4 fault blocks. This entire red area, about 200 kilometers squared, is in communication. We then have some segmentation in the central area, but we still have a connected area of about 30 kilometers squared. Moving through to the P50, you can see that the connected area is now about 160 of this red block, and we've started to integrate some or include some more segmentation between the faults as we move through in here. The P90, you'll see the difference between the P90 and the P11. The P50, sorry, is 11 to 13. So we only introduced 2 more fault blocks by moving through from the P50 to P90, suggesting that the P50 is going to be a suitable maximum approximation. Okay, the other way that we can visualize this then is looking at histograms. So each of these represents a case that we've generated, and we're now reporting our P10, 50, 90 according to fault blocks. Again, as we just saw, our lowest P10 is 4, the P90 is 13. So the range between the P10 and the P90 is quite high, so from 4 to 13. Even though there's a small number of fault blocks, we have a greater range, so the uncertainty is quite significant within here. But looking at how close the P50 and the P90 are together, perhaps if we're talking about structural modeling, we might just take forward one of these cases. Maybe the P50 would be sufficient to incorporate that uncertainty. But it's that sort of analysis that you can do at this early stage, just based on that interpretation, to figure out how many structural models you should be taking forward. Okay, now as I said previously, or as I showed earlier, we had the 2 vintages of interpretation. So this was our initial interpretation. I now have version 4 auto-tracked. And if I toggle that active, you'll see there's a whole host of more faults in here, and also quite markedly increase in the number of fault blocks. So 3-fold we've increased the P50. The P10 has gone from 4 fault blocks to 22 fault blocks. So the first thing we can look at is that histogram. I'll come back to that. The first thing we can look at, is the quality assessment. So taking that new interpretation, you'll see that the score has gone down. So it's saying that the quality of that interpretation has increased. The confidence can be high or higher in here. We've got a greater number of faults, but a lower number of issues. And most of the faults are now, or most of the issues are now showing as medium or low. So we know already, just by quickly running this, that we've got a better interpretation. We've got a higher quality interpretation. If we look at the histogram, P10 to the P90 range, again, although the total number of fault blocks has increased, the range between them has significantly decreased. So again, the uncertainty associated with this has decreased. We might want to pick out maybe one. We could maybe take a P10 and a P50 forward specifically in here, because there's not a large difference between the P50 and the P90. So this is just a way of identifying the type of models that we might, or how the number of models that we might want to take through to do our uncertainty analysis on. Looking again at that fault that we were reviewing previously, look at the whole fault, you'll now see that we filled in all the interpretation, and we're still getting exactly the same segmentation within here. If we just zoom in and flip between the P50, you can now see that we have really started to segment up the field here. This whole thing in the P10 and the initial interpretation was an entirely connected 30 kilometers squared area. Now, if we go into the P90, it's made up of a lot more different fault blocks at sort of 6 kilometers squared. Okay, so if I just zoom out, another way of visualizing this then, here we're looking at the total number of fault blocks. The other way that we can do this is look at the connected area of wells, connected areas to well or location. So you can just see it graphically within here, or you can select this option and then input the well. You can see here I've put in well bore AMN01, which is this black well penetration within here. And in this time, the histogram now tells me the area connected to the well as opposed to the total number of fault compartments. So I've got a P10 to P90 ratio of sort of 30 to 9, so it's just over 3 to 1 for my initial interpretation. I just see what that's doing. It's showing that, again, this entire compartment is connected, whereas if I move through to the P50, the P90, in my initial interpretation, I've actually got a connected area of about 10 kilometers because this fault closes up and causes some compartmentalisation. Let's look at the version 4 auto-tracked, and again, in this case, our P10 has got a far smaller connected area, so it's halved in size. It's now 15 kilometers squared, as you can see in here. But more importantly, the P50 is now being reported at about 6 kilometers squared. The P90 gets no smaller. We just zoom into what's going on there. You can see there's now these internal faults within that main segment that are connecting up and forming further compartmentalization. So going from sort of a P10, if you remember our raw case, is even smaller than this. We've got a connected area of 30 kilometers, whereas our advanced interpretation, we have a connected area of about 6 kilometers squared. Okay, so that's you could leave it here. You could just use this as sort of a graphical analysis and sort of a quantitative analysis of how connected our reservoir is. But you'll also notice in here that I have the ability to export any of these thumbnails. So whether it's the P10, the P50, the P90, I have an export to Petrel option in here. So I'm going to export every 4 sticks, spaced approximately 100 meters. So I'm just going to go back into Petrel then and show these. So for each case, in my input pane, I then get a folder that's named AVA structure, P10, P50, P90, etc. And then just turning those on to show what they look like. So what we're doing here is we're taking that initial fault interpretation, we're applying the fault tip extensions, connecting up the faults appropriately, and then we're also applying some smoothing, essentially to make them fit for purpose to go through to things like the structural modeling workflows. So automatically, you can see very quickly that I've generated this connected fault network with my fault tip extensions that's fit to go forward to modeling. If I turn those off, the main faults, you can see that all those have been applied. We're not going to get any of those error messages. There's no fiddly pillar gridding that needs to be done here, and we can take these forward. So I'm just going to show how this output from AVA structure then can be used within the structural modeling workflows within Petrel and build up, as we said, those different structural models. So let's say from our initial analysis, we have 2 or 3 structural models that we want to take forward. I've just opened up a structural modeling workflow and just using the workflow manager in Petrel because these faults that we just showed can be directly gridded up using the fault frameworks. This fault framework can then be fed into the model construction to create a structural model. We then create a depot space calculation, so we return that back to depositional space. We can then build our depot grid, our structural grids. So structural gridding in here, you can see that I've output the P10. And what I've done is I've taken the raw interpretation data, I've done it with this. I've created a P10, a P50, and a P90 model, which you can see in the background here. So the top left is the raw interpretation, and you'll see that I've added in a little point in Petrel. This red point is the raw fault tip. So this is how far the fault will propagate without any fault tip extension. I then created the P10, top right, P50, bottom left, and P90. Again, automatically within Petrel using that output of AVA structure and then the workflow. Oops. So let's just zoom in and see what this is doing. You can already see in the P10, we've extended that fault tip by quite a significant amount relative to the fault. But in the P50, we've nearly doubled that fault length. Again, this is all done automatically without any need for horizon cleanup, etc. And in the P90 case, we've extended and essentially closed up this entire compartment. And you can see that on all the other faults as we move from here down to here, etc. This is, excuse me, actually the AMN01 fault within here, well within here. So you can see very quickly, I'll just show the models. Very quickly, I can build up these structural models. So in here, these are our structural frameworks. So P50, P90, P10, as well as the raw one that I've then run through the depot space, the depot gridding calculations to produce what we call depot grids that sit in here. And these grids can then be fed directly into the uncertainty analysis workflows. We can populate these with our patch physical properties and therefore integrating that structural uncertainty into our reservoir modeling workflow. The final thing I'm going to show on here is just some top-down maps of that AMN01 well, with again each of the different structural configurations. So top left being the raw data, and as I'm just zooming out on these, just have a look at how those faults are connected up and what the compartmentalisation effect is as we move through to each of the different scenarios. Okay. So you can see in the raw interpretation, essentially this entire, think of about flowing through this unit. If I was down in the down dip area, I could essentially flow through this entire section within here. By simply applying the P10, we firstly close up these compartments, but also this compartment within here. And that's just by applying a P10 confidence extension. So we dramatically change the configuration of the reservoir. Then as we increase the P50 through to the P90, we continue to increase that compartmentalization, but essentially we've already hit a critical point. By the time we hit the P50 with this AMN01, that further fault tip extension isn't going to impact our models. Okay, so just a quick example of how we can build up that structural uncertainty and automate that into the process. And then I'll just jump back into PowerPoint. And the final slide that I'll show is just how this sort of links into the current Petrel workflow. So here I'm showing the interpretation, structural modeling, and gridding domains, and then AVA structure essentially sits below there. So the whole point of this is that AVA structure isn't designed to replace functionality within Petrel, it's designed to complement it. So taking the seismic interpretation, we run it through AVA structure, we can output various structural configurations, structural models, P10, 50, 90s, and these feed directly into the structural framework modeling workflows. From there, we can obviously go to conventional ways or previous ways of modeling, like pillar gridding and stair-step gridding, that are a bit clunky and very exhaustive, or we can utilize the deeper gridding functionality, essentially to automate this entire process and very seamlessly and quickly generate P10, 50, 90 structural models. And then once we're there, of course, once we finish gridding, we can take these forward to modeling, just highlighting the use of AVA clastics and AVA saturation to our other products in the AVA line. Okay, so that's kind of the end of it. I appreciate that was a very quick introduction to AVA clastics and AVA structure, and what we're doing. So we've got about 10 minutes left. I'll pass you back over to Laura and we'll open up the floor to any questions. Thank you all for listening.
Thanks very much, Dan. That was very interesting. It was great to see how we can use AVA structure to address structural uncertainty in our models. We're ready to go ahead and take some questions now. So just a reminder that in order to ask a question, you need to type it in the question box and you'll go to control panel. I'll give you a few minutes to type those out and then we'll start the Q&A.
Okay, thanks guys. A couple of questions here. So the first one is asking us to comment on the sort of why we recommend using the interpretation rather than the structural model. And I guess to help that, I'm just going to go back a couple of slides in here. So there's a couple of things. Number one is because when we upscaling, we go through to the we take sort of bin spacing seismic at 12.5 meters and we apply some smoothing to this. So we move not only laterally up to about 12 to 50 meters in here, but we also then apply some horizon deletion. We remove data, hard data, away from where the faults are are being populated. So it's really that interpretation data close to the faults that is the most important, especially when we're doing this linear regression analysis, because that holds the information to how the fault is actually behaving. We want to be using as close to the raw interpretation data as possible. There are some noise effects that we can filter out. We would always recommend using the interpretation data as close to its imaging resolution as possible, because what we see, if I just skip forward again onto this slide, is that this is essentially just an approximation. It's already been smoothed. We're missing basically about 500 meters of the actual fault before we even start doing the regression analysis. And that's caused by the closing up of this fault close to the fault. What we see is the fault tip here. If you just follow this, you can see all of a sudden it starts diving down into there, and that's because it's being pinned to a pillar within our model within there. So the way that we do that then becomes subjective and opinionated. So there's a lot of human sort of opinion going into here, as opposed to something like AVA-structure, where we develop confidence lines, so a P90 and a P10, sorry, P10 and a P90 confidence line in order to do that analysis. And then we also develop this or produce this probability density function that we use to then control our confidence in the linear regression analysis. So we apply science to the problem essentially, and we do it in an objective way rather than something that's very subjective. So hopefully that answers that question. I do have one more, so I'll just answer this one, and if anyone has anything else, just please type it in the So this was just to do with how long the whole process takes, and well, the direct question is, how long does it take to generate P10, P50, P90 structural depot grids in Petrel? So if I just go back to this final slide in here, so implementing AVA-structure to generate the P10, P50, and 90, this is essentially a matter of minutes. So you can run this and you get your P10, your P50, P90 cases to do the analysis on in a matter of minutes. So that really doesn't take any time at all. To then export it, again, sort of in talking minutes. So to get down to the input into the structural modeling workflows, less than 10 minutes if your data is in a good enough condition. There are obviously the QC alerts that we go through, and there's various quality assurance steps that are recommended by AVA-structure. So there might be more there that you need to go and address, but assuming that your interpretation is in a good enough state, we can do this in a matter of minutes. And then the structural modeling workflows, it's then hours, if that. You could probably run the P10, 50, 90 through the depot grading workflow, as I demonstrated, in less than an hour. Which means you go from your interpretation to a fully functional model ready for property population in less than an hour. And that's why we say that it allows us to automatically or integrate, the structural uncertainty automatically into these workflows, because it is seamless rather than a much more exhaustive process in things like pillar gridding.
Great, thank you for those questions, everyone. It seems like we haven't got any more right now, but if you do have any further technical questions about AVA-structure, anything that's been presented today, feel free to reach out to Dan via email. His email is being displayed currently on the screen on the top left-hand corner. It's dan.hemingway@pds.group. You can also reach out to Mark Fishorin, the product manager for AVA-structure, and his email has also been displayed on the screen immediately below Dan's. We really appreciate you all being here. A reminder that this webinar has been recorded. Attendees should receive a copy via email within the next 24 hours or so. If you wish to share that link with colleagues or friends who you think might be interested in this webinar, then please do go ahead and do so. But we'll also make this webinar available on our website pretty soon, not within 24 hours though. So you'll be able to share it with colleagues and friends there too. This is the third webinar in our Autumn 2019 series. We'll continue next month with another webinar presented by our Subsurface Director, Vicky O'Connor. She'll present a session on how blending high-quality data with proven scientific methodologies can allow subsurface professionals to assess the impact geological uncertainty has on their decision-making. For details of that webinar and all our other webinars, and to register for your spot on those webinars, please head to our website at the address shown below. We thank you very much for joining us today, and we'll see you next time.